Hi everyone, let's get going. This is Sandeep Sharma. I will do a very quick introduction about myself and then we will get started. I'm working about 2 decades of experience in machine learning, analytics, technology areas, various technology areas. Also done plenty of product management. I have worked on solving problems which require classification. So naive Bayes classifier is, or naive Bayes, this is the tutorial we are talking about. Bayes actually was the creator of Bayes theorem, and naive Bayes is an implementation of Bayes theorem. So today I will talk to you about what is a little bit about machine learning. I will talk to you a little bit about classification. Then we will talk specifically about naive Bayes, and then we will do some practice. So it will drive home the concept, because naive Bayes is one of those things which you will only understand if you practice it. The machine learning part, also we have a hands-on where we will go through it and actually demonstrate it. But the real crux of naive Bayes, if you ask me, is when you practice it, because there is a lot of probability into it. All right, so what is machine learning? So naive Bayes actually is a part of machine learning classification algorithms. And what essentially is machine learning? Machine learning gets thrown around a lot. Machine learning is really about the study of algorithms, and those algorithms we use because they can learn from data and they make predictions. So what is it that we want as outcome from machine learning is ability for the machine to learn and give us a prediction, a decision, an information intelligently. So it uses computational statistics. And what is computational statistics? There are a few top 4 areas where machine learning comes together. Top 4 areas of mathematics, I would say, that come together to create machine learning. The first and foremost is linear algebra. This is the science or the math of operations on matrices. So it could be a multiplication of matrices, it could be a addition of matrix. Usually it is dot product or multiplication of matrices. And a lot of what you see in machine learning frameworks and you see hardware like GPUs, etc. They are all primed. They are all tuned to do matrix operations very quickly. They're designed for that purpose. So that's one. The second one is probability. And today we are going to understand how probability, this is just one of the examples we will see where probability is applied. Probability is applied in a lot of different ways in machine learning. And the third is distribution. So how our data is, what is the distribution of the data? It could be a normal bell curve distribution or Gaussian distribution. It could be other forms of distribution too, like binomial, etc. Yeah. The fourth one is calculus, differentiation or integration. Differentiation, especially when we are trying to find some of the terms which are used in machine learning, for instance, stochastic gradient descent. A lot of optimizations, and SGD is one of those optimization means, is through differentiation, by breaking a problem down into smaller and smaller chunks and then moving towards a goal. So this is machine learning. It has applications in many ways. Speech recognition is the best example I can think of. Is you using your phone, voice command on your phone, either with a smart assistant or simply typing. That is speech recognition. The second one is face recognition. Again, if you have face unlock on your phone, that is an example of face recognition. The picture we are seeing here is cameras being used to detect people walking through an area. So, okay, this is staff, for instance. This says it is staff. Um, so you could have people walking in and a camera being placed in an office which detects that this is a member of the staff. So you potentially would not have to carry something like a lanyard around your neck, or it just recognizes you. There is no other need for any other thing. Then it's also used in antiviruses, which is interesting because when people are doing some hacker or somebody is trying to create vulnerabilities or make some damage to the system, then these antiviruses earlier had standard definitions. Okay, if this happens, and they had thousands of those. If this happens, then this is a potential antivirus. But the smarter antiviruses of today and the future actually look at behavior, what is happening in your system. For instance, if suddenly some kind of files are getting created, then that is potentially example of antivirus. And then you have weather predictions, and this has been one of the primary uses of machine learning even before it had become so commonplace. So we talk about machine learning a lot now, but this weather predictions have been using models, and the most advanced models using data. For instance, this is fog, partly cloudy. I mean, it uses weather conditions and data to make predictions for the future. And these advanced models have been around for decades, constantly getting improved. Two kinds of machine learning: supervised learning and unsupervised learning. These are the two broadest categories. Supervised learning is typically where you have there is a supervisor. Think of it as a supervisor who's telling you to do this, yeah, and then you learn on your own. If you were to work on a job, you would have a supervisor who will initially tell you a few things and then you learn, right? So think of that as that way. The definition here is, so classification is an example of supervised learning, and classification is where you have some known labels. The example here is a fruit classifier. Say orange, apple, and banana. You were told that this is an orange, this is an apple, this is a banana. You could easily your machine learning algorithm can then learn these three different types of labels and be able to predict. But unsupervised learning is slightly different. Unsupervised learning, nobody's telling you. So a good way to think of it is clustering. Clustering is the result is really you do not know these three fruits, but you can distinctly see these are different. So if a baby or somebody who's not in this world, it comes from outside, they can also potentially see that these are three different fruits, right? There are fruits with soft skin and a lot of dimples. Now, the machine learning, the system will not tell you that this is a fruit with soft skin and a lot of dimples. But it will say this is a cluster A, cluster B, cluster C. Yeah, or basically three different kinds of clusters. It will be able to identify that. Now, why is unsupervised learning required? Number one, a lot of cases you do not have labels. It takes a lot of effort to define things correctly, label them. So for instance, today, if you were working in a company and you were to start doing some, I will do a machine learning to solve this problem, the first thing you will ask is, I need label. And typically machine learning, for machine to learn, it requires a few 100,000 or a million data points. Now if you're going to use hundreds of thousands of data points or data, then if somebody has to label all of that, it is a lot of work. So therefore unsupervised learning actually has seen immense progress in the past few years. Introduction to classification. Classification is really simple. Classify or set categories. So if you were trained, for instance, on the fruits, and a new fruit is given to you, it could be watermelon. Well, if you were only trained on three fruits, and you're doing classification, you'll probably either say it is one of the three categories, or it is a new category altogether, because it doesn't fit in any of those categories. So yeah, that's classification, as simple as that. It is based on training set of containing observations. This is examples of classification. Is it A or B? Is it dog or cat? Will it rain tomorrow? Is a transaction fraudulent? Okay, these are different types of algorithms, and each algorithm is a class in itself, so I will not go into that. But I'll just say, linear is the one which is of interest to us. A linear algorithm is simply a means for us to where the classifiers are directly, impact the classification. There is and let me say, some things are explained better by the other means. So decision tree, for instance, works on um, nodes and leaves. You are at point A. You could even either go to B or C. Then if you choose C, then you could either go to D or E. So it's like a tree. So there are linear classification algorithms. There's naive Bayes, there is logistic regression, and there is perceptron. Again, each of these requires a lot more understanding before I could simply explain it. So we'll just focus for today on naive Bayes and dive right into that. So naive Bayes is a form of so Bayes theorem is the parent for naive Bayes, and Bayes theorem was designed by a person named Bayes. He was a minister, which is in England, which is he was really a clergy or a priest. Yeah. And he designed the naive Bayes theorem. This is the formula of naive Bayes. It is a condition when the probability of A happening given B happens is defined by this formula. Why is this formula so important? It has practically created a separate branch of data science in itself. So Bayes and Bayes models and Bayes tools are one separate branch of data science. While you have frequentist methods, there are Bayes methods and experts on Bayes and tools on Bayes. So let me explain this a little bit further. You need to understand three concepts of probability to be able to understand what's going on here. So number one is conditional probability. And what is conditional probability? So first of all, let's just say probability. What is probability? Probability is the chance of something happening. So we also call it, so PB, for instance, here, we will be calling it as marginal probability. Marginal probability is nothing but the probability of B. So it's just a fancy way of saying that. And why is it important? Why is it different from conditional probability? Because this is unconditional. This is just the probability of B, irrespective of whether you have something called A or not. Yeah. But probability of B given A, when A happens, then B happens, is conditional probability. Why? Because when A happens is a condition. So this is conditional probability. Number three, so there is marginal probability, which is like the basic probability, unconditional probability. There is conditional probability, and this is also an example of conditional probability. A happens when B happens. And there is joint probability. These two, by the way, both of these are marginal probability. There is joint probability where the probability of A as well as B happening. So it's joint probability, and joint probability is we'll not go into the derivation of all three, but we just need to understand these three probability concepts. So what is naive Bayes? And let's just go through an example. So I have some data, based on which I want to decide whether I can play or not play. So it could be season. So it's summer, monsoon, or winter. Is it sunny or not sunny? So you could have sunny even in summers or in monsoon or in winters. And is it windy or not windy? So you could have wind blowing in any of those seasons. So based on these data points, I want to be able to say whether I can go out and play on certain days. Now, how do I do that? I have some an idea of, some days I can go out and play because, well, weather was monsoon, but it was not raining. So, well, it was sunny, and there was wind blowing or not blowing, so I could go out and play. So I collected some data. So I am then going to use that data to apply what is called Bayes theorem. So here we have an example. So this is the seasons. Yeah, this is the whether it is sunny or not. So I got two dimensions or two features, season and sunny, not sunny, and I am plotting some yes, no, play or not play. So this is play, all the blue lines, the big circles, and this is not play. And I want to be able to predict whether I will be able to play when there is no sun and it is winters. How do I do that? I actually create a frequency table. Typically, how would we approach this? I would say, okay, if you notice in summer, it is advisable to play when there is no sun. So summer, no sun, but he's still playing. So this is great. But summer, it is again no sunny. It is not windy. So I'm not getting into why it's not sunny and not windy. So therefore, why he's not playing. It's just that the data says that in this case, although it is summer and it is not sunny, I'm still not playing. So what happened? Yeah. So again, this just shows that different conditions impact my decision. We've talked about everything. Bayes is an probabilistic classifier because it uses probability. It applies Bayes theorem, and it is a strong. It Why is it called naive? This is a question which arises. Now, why it is called naive is it assumes that B and A are independent. Their behavior is independent. They are independent events. Yeah, where B and A are events, and P probability of B is not equal to 0 because this is the denominator. Yeah. So independence assumption is very, very important for naive Bayes to work. In most real life situations, independence does not actually, it doesn't really happen. Yeah. So if I really wanted to explain in a different way, if I don't, but I can take that as an assumption. It simplifies a lot of things for me. So I will take, I took that assumption to solve a problem, and I arrived at this is the Bayes, theorem again mathematically, as I said. Let me take a little, next slide and explain this. So these three, again, if you see this as the A B that we were talking about, same. This is the same formula as this one, yeah. But in practice, how do we apply this? So C is the class that we are trying to predict in this case. And what is a class? The class is whether I will play or not. Yeah, that's a class. A decision could be, let's say, if I like, for instance, this is used in spam detection. Knife Bayes is used in spam detection. Spam detection. The example would be, if I see a mail, if the system is fed an email and it is fed thousands and thousands of email, it needs to be able to detect spam on its own, and it does that and says spam or no spam. So that is C. It is the output or decision that we are expecting from the system. Yeah. X is the condition or input. So X is sometimes it is called predictor, estimator, different things. There is different words you might come across, all fancy ways of describing the same stuff. So don't worry too much about that. Another way to look at naive Bayes is, so we have this C's and X's all over, right? Another way to look at naive Bayes or Bayes theorem in itself is, it says that in life, I have some understanding of, let's say if I'm going to be predicting spam, I have some information or some intuition about how to predict spam. If I asked you, without having read anything about how spam is detected, you will say, well, there are, if I were given the job, if I see somebody saying you will earn $1 million if you and I want to, you've got a lottery, I just want to contact you and transfer the lottery to you, please click on this link, you probably guess that this is spam. Whereas if this mail came from somebody you knew, your friend, which says we talked about this, and these are the three things I will be doing, so let's talk again on Friday. It seems like you know that it is genuine. So there is that data or that intuition, we call it prior probability. Yeah. So this is prior probability or prior information that we have. Then if we had that information, and we had in some ways, this is called we had some intuition and we had more data. Yeah. If we had more data about that, then it would help us to get even better at our decision making. So this is prior probability, means we had some intuition. Likelihood or evidence, this is also called as evidence, means that we have some more information or some data. So we convert that, whatever data we have, we convert that into a probabilistic model or number, and it tells us a posterior probability. Posterior probability means it is the new probability that we have gained based on uh, applying prior as well as new information or new data. And that's how that is the reason it is called posterior probability. This is also called as and this one, we said this is nothing but predictor prior probability. In most cases, and we will see this today, in most cases I don't need it, I actually am able to manage without it. The reason being, it's a constant, because I'm going to compare two pieces of information. It's a constant for me. So typically there is a proportionality between posterior and likelihood and prior. Just remember that. And another way to look at this is, I have some prior intuition, prior information, I am going to get more data, and I get posterior probability. Now those prior intuitions, how do we apply that? We will talk more about that. This likelihood is also I was saying, this is also called as evidence, because it is new data for me. Yeah. I have this formula. Yeah. And I have this data, and I am trying to predict something. So the problem statement here is, we want to use naive Bayes to decide to predict whether to play football. This was data about whether I can play football or not. When the season is winter, it's not sunny and it is windy. Season is winter, so this one, it is not sunny, so sunny no, windy yes. So I want to predict this, and I have some data points from earlier. So sunny and season, sunny and winter, and season, sunny, yes, no, and season, where when there is no, it's not sunny but windy, then what happens with different seasons? So we have tried to, in two dimension, we have tried to understand these different three main predictors that we have, which is season, sunny, and windy. So I am going to, what I need to do that is prepare, this is the groundwork. I prepare a frequency table. I have three frequency tables because I had three predictors: sunny, windy, and season. And I'm saying whether I will play or not play. So I have two values for sunny, yes or no, same for windy. And I'm basically saying, because my outcome that I'm trying to predict is whether I'll play or not. So I have created the frequency table using the predictor and using the classes. So how does the predictor interact with the class? So predictor interacting with the class, and I have some information on this. So you can consider, if you were given this information, either you will prepare this information or you will be given this information, and then how do you go from there? Typically, to get to this point, is there will be some work required to extract data and put it in a format where you can actually say, okay, in real life, if you have a real naive based problem, you will probably have tens or hundreds of different predictors, and you will have, this is a binary class, yes or no. you could have multinomial classes, which could be, it could be many classes. So it could be like, fruit types, right? Apple, banana, orange, mango, and so on and so forth. But this is what we have. So we work with this. So I created this in this form, because I had, actually this is the precursor to the frequency table. So when the season is this, do I play or not? When it's windy, do I play or not? And I pretty much create a data sheet like this. If I don't have information, I'm going to use that to predict. So going back, so basically different days, and this actually I combined the data sets from here, so therefore I haven't put, you know, but we have in all, in this frequency table, let me go back here. Yeah, I have 3 days when it was sunny and I played, 9 days it was not sunny and I played. So overall, 9 plus 5, I have 14 days worth of data in all these three places. Okay. So this is 3 plus 6, 9, and 5, 14. This is also 3 plus 6, 9, and 5, 14. So 14 days of data I have, and I'm going to use that. What do I do? So I'm going to do two things. I will calculate the probability of play, and I will calculate the probability of not play, and I am going to say whether whichever probability is higher, I will use that. The problem is frequency table. We define the problem in terms of frequency table. Then we go into, I have created a sheet for myself, just to explain this, because it is something which needs, working. I put this in terms of base formula, and the base formula is, we said P of A given B is equal to P of B given A multiplied by P of A divided by P of B. Probabilities. These are all probabilities. Yeah. Now, how do I populate these probabilities? This is conditional probability, probability of winter multiplied by winter given play, probability of not sunny given play, and this is what I'm trying to populate. And how do I do that? I use this. So probability of winter when I played is 2 out of 9. Probability of summer, of monsoon when I played is 4 out of 9, and so on. So our problem is very specific: winter, not sunny, and windy. So yes, windy, yes. Yeah. So 2 by 9, and not sunny is 6 when I play, 6 by 9, and then again windy and play 6 by 9. Yeah. So this is our probability. Conditional probabilities or likelihood. I use this 2 by 9 multiplied by 6 by 9 multiplied by 6 by 9, and then I have to find out the probability of play. Probability of play is, it will be same in all cases unless you don't have data for somewhere. 9 days out of 14 days I played, so I will put that in, and then I have the prior predictor, which is P or B, as you were saying. But this is probability of winter, probability of not sunny, and probability of windy. How do I get that? Probability of winter 2 by 5, 5 over 14. Probability of not sunny, so this is 7 over 14. Probability of windy, this is 8 over 14. I plug all those numbers, I get 0.6223. So this is probability of play given winter, not sunny, and windy. I will also find out the probability of not play, and the probability of not play, again given the same three conditions. I get probability of winter given not play, probability of sunny given not play, no sunny and no play, and probability of winter given no play. Multiplied by my prior now is no play, not earlier it was play, now it is no play, because I am trying to find the probability of this. And this is divided by probability of winter, probability of not sunny, and probability of windy. Why I was saying this is a constant is because when I compare these two, to make a decision on whether to play or not play, this denominator remains same. And that is why I actually did this exercise for not play, just to show to you that this actually doesn't matter. What matters is these two. So really, if you are able to calculate these and you get the number, uh, it is pretty good in absolute terms, because the probability is greater than zero point 0.5. Yes, you need this number, but typically you're going to be comparing. This is binary, as I said, whether you are play or not play. If you had more, then you would compare all and you would ignore the denominator. Now I'm going to plug the same numbers here too. Here, probability of winter given no play. Winter given no play. So 3 out of 5. No sunny is 1 out of 5. And windy is 2 out of 5. So I put all those numbers in this, and I get basically put all those numbers, I get 0.28. So which is, this is more than, this is less, and probability of play is more, so you are good. So you can go out and play. All right. So the problem here is, if a single card is drawn from a standard deck, the probability, so a deck of cards has 52 cards, and if you have done a little bit of probability earlier, you probably solved this problem earlier. The probability of that card is a king is, so essentially the problem we are trying to solve is, what is the probability that the card is king given it is a face card. Now a face card, there are three face cards in cards, right? Either it's a king, it's a queen, or it's a jack. The probability of it being a king is, intuitively it is 1 by 3. We are going to solve this through probability, through naive Bayes. So probability of king given it's a face, probability is, I'm again putting the formula, probability of face given king multiplied by probability of king as the prior, and probability of face. So probability of face given it's a king. So we know the probability of a king card is a face card. So if it is a king, it is a face, this is probability is 1. Then the probability that it's king. So we have 4 kings out of 52 cards. So the probability is 1 by 3. And the probability that it's a face card is, we have 3 face cards, and there are in each color or type, whatever. And there are actually 12 face cards in out of 52 cards. So 12 by 52, that's the number. So which becomes 3 by 13. So I put this in a formula. So probability of king given face is equal to probability of face given king, yeah, multiplied by probability of king, okay, and this is divided by probability of face, right? So what do we have? We have, if I were to try and populate all of these, this I do not know, so I'm going to calculate this. Probability of face given king is 1. Okay, probability of king is 4 by 52, which is actually 1 by 13, 1 divided by 13. And probability of face is 4 times 3 divided by 52, which is actually 3 by 13. It's taking this as a, I just want 3 by 13 equal to, yeah. And this is 1 by 13 equal to 1 divided by 13. Quickly do number. Okay, so I am putting this formula here, and let's see, I get this multiplied by this, divide by this one. And it is, as we said, it is 1/3. That's what we found out from intuition, or from our roundabout approach. Same we get from naive Bayes. So you can try and do naive Bayes. I will jump into a hands-on some coding. So I did this coding on Collab, which is an online notebook provided by Google. You can also get yourself a Collab. It is hosted by Google. You do not have to install anything, and it works beautifully. So I think there is every reason for make the most of that. It gets you started, like snap of a button of your fingers, and if you have a Gmail account, you will get a Collab account. Just go to Collab. I'm bringing the site now. Yeah, so this is collab.research.google.com. If you go there, you will be you will get a lot of different options. So just see what it does. This is a Python development environment, essentially. Just like you have other environments I can name are PyCharm, Anaconda, and people use Jupyter notebooks. The only difference here is this is hosted by Google, so it provides you a notebook environment, that a notebook that you can share. You can you get a ipnb file. You can actually share that notebook with others. So it's pretty cool, and I'm just waiting for it to come up. Okay, so here we go. I will bring up a notebook that I was working on, which is this one. So I've done the coding already. We're just trying to get to. We'll try and use that code, and I'll walk you through this code. So this is a program where I am going to talk to you. So an application of naive Bayes. So these are the different columns: gender, your SSC percentage, SSC board, HSC, which is, this is, I guess this is 10th, this is 12th, percentage, board, what subjects in HSC, degree, percentage, degree, title, work experience, yes or no, entrance test percentage, specialization, MBA percentage, and then status, whether. Uh, so this is the outcome, as they say, and these are the inputs or the predictors or estimators. Okay, these are all the predictors and estimators. This is really just serial number, so we will probably not use it. Okay, going back here, I have this notebook. I have to import this in my Google Drive first to be able to use it. So I will do that by using this command, where I actually have to first mount the drive on Google Colab notebook. So there is a command for that. You can pretty much ignore it for now. We'll focus on the rest of the stuff. I just want to make sure it is mounted. And if it is not mounted, it will say go to this URL. So if you put this, because you will have a Google Drive. If you have a Google account, you will have a Google Drive. And when you open a Google Colab, then you will get that. So it will sign me into my account, and I will essentially, this is the Google file stream. So there is just some work that needs to be done. So I get some code that I copy here, yeah, and it starts working for me. And this the spinning wheel stops. That means I am good, mounted at content drive. I have to import certain libraries, so I will import a pandas library to get the data in. Pandas is a way for you to build the data pipeline. I will import NumPy, which is another Python library to manipulate data, do some operations, and Seaborn and Matplotlib. These are visualization libraries, so we'll make use of those. And then there is scikit-learn, which is a large package. It has a lot of functionality. One of the main functions. So one of the popular uses of scikit-learn is to, if I get data, I have to split it into train and test. And why do I have to do that? Because if I have data, let's say I got 10,000 pieces, data points. How do I know that my program or my model works fine. So I do that by saying I will train on some data and then I will test on some data. When I do that testing, although I have information about the data, but I'm going to compare what is existing versus what my model predicts. So what is the truth versus the model predicted outcome? So if it was spam, I know this is a spam. I had people tell me that this is a spam, and then my model says this is a spam, then it is good. If my model says this is not a spam, then it has missed something. Yeah. And then based on, if I had 10,000 of those, I typically do a 80-20. So 8,000 I train, and on 2,000 I test. And out of those 2,000, if all predictions are right, then my accuracy is 100%, and I have other metrics. But if it is not, then I see how close it is to perfection. So is it 99, 98, and whatever metric we take. So will not go into that, but this was the essential objective. Now we have scikit-learn. So we also have, as I said, besides accuracy, there are other metrics like confusion metrics. We'll talk about that when we get to that. So let's just get started. So I got this library. I did all the import. Don't worry about this. This just a warning. So it worked fine. And then I had this. I have this file which I actually uploaded on my Google Drive. It's on my Google Drive and on a path like this. So I just do this. So basically, I read the CSV file. This was a CSV file, and I read the CSV file, and I'm going to check if it worked fine. So this is a data frame, pandas data frame that I am reading. Let's see if it came out okay. So um, the same thing that we are seeing here is being shown here. So I've imported the data successfully. This has 215 rows and 14 columns. The 14 columns are the features or the predictors, and one of the columns is the dependent or the outcome. Status is the one that we are trying to predict. So I have some historical data. I want to make use of that. So one of the things I want to check as part of my groundwork or pre-processing is to see if I have any null values, any like is gender not defined, is percentage not given. So I find there are no null values, which is a great thing. That means I have good quality data. Again, let's move. Now I just want to see how many people got placed and not placed as per this data set that I have, the 215 students. So I have some number. I can see people who got placed over 150, 140, 150, maybe 145, and not people who did not get placed. So this is me using the Seaborn to do that. So after that, I am going to convert. So I have some categorical variables. For instance, work experience, right? These are some categorical variables. Let's say I filter this data, and you could start. You could actually use Excel if you have little amount of data, like thousands, because Excel has a limit after you know I think a million, it cannot handle any more data. So I have male and female in this category. Similarly, work experience, whether it is yes or no. So I know what are my different categories. I will pull that in here. And so work experience, for instance, was my category, work X. What I want to do is convert that, because the system doesn't understand whether workx is yes or no. It understands only ones and zeros and basically numbers. So we convert that into indicator variables. Variable, for instance, if you have workx, then it is 1. If it that is a default way we handle it. If it is you do not have workx, then the value is 0, and that's it. I want to check what happened with my workx. I want to do that, and I will, let's just see. So earlier I had work X yes no, and now I have, did I not run this? Yeah, okay. Okay, I ran the code, and now instead of yes no, I have two columns for work experience, which is uh, where you have no's and where you have yes. Yeah, actually I could have done with one column too, and I can even delete this as this was just for I could have done with one column too, but I just wanted to you know I used two, because one column in the sense it anything which is not work X, I can make it 0. Okay, all right, then I want to concatenate data from the original data set. I have some data which is I want to drop from this section, just because I think that this is redundant data, not useful. So I'm doing that, and this is some code that I have used pre-built, so that is part of the reason. After that, I have I got my data frame df. This is the data frame we defined. I have dropped some columns, so my data frame is much more lean now. It has got much less columns, right? It has got only percentages and status and work X. So this is all that we have for use. All right, so it's a leaner version now. Again, I remove this, and now we can see. So we have two: the predictor X and the independent or the outcome Y. So in predictor, I'm dropping status because I don't need status in predictor, and in Y, I am data frame will only be status. And then I have divided that into train and test. My both my input as well as my output is divided into trains. Basically, I've like sliced it at a certain point, and that size is 0.3. The test size is 0.3, which means the train size is 0.7. So 30% of my data is test data and 70% is train data. And I have done that, I have put a random state 1, which means that I have not gone and done it at I have done it randomly. So 30% I took from a bag and put it as test, and the remaining in that bag remaining I left as train. After this, we have we did the train test work just to prepare this data for training and testing. So this is the code that we did. Now we apply naive Bayes theorem. Again, while we did the hard work and we did all of that, here it is pretty straightforward. So we apply naive Bayes from sklearn dot naive Bayes. This is the method that is called, and we import Gaussian naive Bayes. So Gaussian naive Bayes is nothing but a naive Bayes method where Gaussian means it is normally distributed. So your model could have different distribution. The example that we have about play not play, we had very little data, but in some cases that data could come from different kinds of distribution. It could be, as I said, it could be binomial distribution, it could be Poisson distribution, Poisson, and so on. But Gaussian is the most common and popular. It is nothing but a fancy way for normal distribution. So we did that. We did model initialize, and then we fit the model for train first, and that's it. This is done. Now we compare and the prediction. Use the model to predict. We've trained it, and now we will use it to predict on data on X test, which is the input, and let's see what we get, and we will compare with what we already have. So Y test is what I already have, the actual status, and using X test and model prediction, meaning the model does its work, I get Y predict. and let's see what we get out of it. Okay, so I need to do df. So df1 is my new data frame, and let's see what it gives me. So this is what it says. So placed, not placed, placed, not placed, not placed. So you can, forget about this. But important thing is I did randomly because, I did not take 200 onwards or 150 onwards as test. I just picked randomly, and this is what I get. Looks good. Almost everything is matching. So 65 rows we have actual and predicted seems good. Let's see. Yeah. Let's see. Okay, then I print a report, which is a classification report. This is more detail on the same thing. Yeah. So a classification report, I will build a precision recall F1 score. These are slightly advanced, and I think this requires some explanation on its own. But just to suffice that it is not enough to get some accuracy. We also want to know what was missed. And there are true positives, true negatives, and false positive, false negative. So we want to understand all of that before we can say that accuracy is enough. Case in point, if you have, let's say, a medical condition, if you built a model to predict say cancer, well, 99.5% of the people don't have cancer. So your model, if you did not do anything, if you didn't write a single piece of code, you will be right 99.5% of the time. So does that mean your accuracy is good? So therefore we use precision recall F1 score to identify that. Another way of putting that is confusion matrix again, and accuracy score is straightforward. This is percentage accuracy that we got. We were seeing everything was fine, but actually the accuracy is 87.7%. With that, I think I would like to just say thank you everyone for your time today. I appreciate you joining in. Again, thank you very much.